Hello everyone, welcome back to Bytes of CSE. So in this lecture, we'll talk about support vector machine, which is a powerful and versatile supervised machine learning algorithm, which is used for both classification and regression. Though it is used a little bit more for classification, we generally don't use the regressor much. Now this is particularly helpful in handling a complex data set, especially those ones with high dimensions of data. So, if I have to draw a kind of real world analogy, I'll talk about this. So, suppose you go to a nightclub and there's a crowd of people gathered around. Some have a legitimate pass to enter into the club, while some others are just trying to sneak inside it. So, you will need a bouncer who will draw a line that best separates people who can enter from those who cannot. Now this line is known as the decision boundary, and the bouncer would like to draw the line in a way so this is like it would be as far as possible from the closest people on both sides. So he'll try to maximize the margin in order to give the most robust decision. Now we'll move on to the core concepts of the support vector machine. So the first thing which we were talking about, so this is the diagram which I actually talked about right now. So there are two types of balls, the blue balls and the red balls, and we have a line that separates the two colors. So the first thing which we'll talk about is the optimal hyperplane, or the decision boundary that I was talking about. So this is the structure that best separates the data, like the data points which belongs to different classes. Now, right now you can understand that I am talking about the classification aspect of the support vector machine. I'll talk about the regression later, but since classification is used more, we'll understand the core concepts of classification more. So support vector regressor is also based on these concepts. So this will also help when I'll talk about how regression works here. So if your data is arrayed on a 2D space, it will be a line, like the optimal hyperplane will be a line. If it's a 3D space, it will be a plane. And if it is an n-dimensional space, it will be an n-1 dimensional subspace that divides the data. Next, we were also talking about the bouncer will make sure that the margins, he maximizes the margin. So this is another core concept which says that the SVM algorithm tries to find the hyperplane that has the largest possible distance to the nearest training points of the classes it tries to separate. So maximizing this margin will help to improve the generalization ability of the model. This will make it more robust. It will also be less prone to overfitting. Now there are two types of margins, or two approaches by which we calculate the margin. One is the hard margin classification and the soft margin classification. So when we use a hard margin classification, or the hard margin SVM, the data points will be perfectly separated. But this is a little bit difficult to implement in real world, where often two classes of data, they can, if you project them onto a space, they might even be sort of overlapping. So at least some of the points might be overlapping or fall into more nearer to the other class. So in this case, we'll be using a soft margin SVM, where it allows for some misclassification, and this is naturally more flexible. Now these margins, how these margins are actually calculated, it can be explained in more details, but it will make the video more longer. So if you want me to discuss this in detail, please do let me know in the comments. I'll make a separate video on this. So coming back, we are talking about support vector machines. So what are the support vector that we are talking about? Now support vectors are the critical data points that lie closest to the decision boundary or the hyperplane Now, these are the data points which are most difficult to classify and directly influence the orientation and the position of this optimal hyperplane. So, in this context, you can say that these are those support vectors, and the thing is that if you move a support vector, it will the optimal hyperplane will also adjust a bit. But if you move a data point which is not a support vector, it will have no effect on the position of this optimal or whatever hyperplane. And next we'll talk about linear separability. So the arrangement of the data also is very important, because if your data is linearly separable, that is, the data point can be separated by a straight line or a hyperplane in the original feature space, that data is said to be a linearly separable data. So in this case, a linear SVM can be used, but in real world, the data is not linearly separable. And this is where we use the kernel trick. So this kernel trick is basically, it allows the SVMs to implicitly map the input data into a higher dimensional feature space, and in that higher dimensional feature space it becomes linearly separable. And here we actually perform, like we do a linear classification on this higher dimensional space. Now this is actually computationally very expensive to actually do this transformation, and therefore we use some special function which are known as kernel functions to map that to the higher dimensional space. So this is known as the kernel trick. And now let's know a little bit more about the different functions or SVM kernels that we use. So SVMs, as I said, so it's a mathematical function that calculates the similarity between the data points in the transformed feature space. So the first thing which we'll talk about is the linear SVM. So this is done when the data points from different classes can be perfectly separated by a straight line in the original feature space. So this is the function, the mathematical function which is used. So x1, x2 are two data points, and this dot product, it calculates the similarity between the 2 points. And now we'll move on to those kernel which deals with non-linear data. So the first function we talk about is the polynomial kernel, which is basically an extension to the the linear kernel. So this is effective for non-linear data, but this is not so efficient like the other kernel functions which we'll talk about next. So this is the function. So here d is the degree of the polynomial and c is a constant, this c and d that we can see here. The next kernel which we'll talk about is the radial basis function, and this is the most popularly used kernel, or the most widely used kernel, you can call it, for SVM. So this maps the data into an infinite dimensional space. So this makes it very effective for complex non-linear decision boundaries. And this is the equation, or this is the function where gamma, this is the parameter that controls the influence of each training example. So this is exponential minus gamma, and this, if you're wondering what is this is actually the L2 norm, or the Euclidean norm. So if you remember, I have discussed about it in the other video. So if xi minus xj, suppose that I consider as y, so this would mean, this particular thing would mean root over, this is summation yi, where I equals to 1 to n. This is only for this part, okay, not the entire thing. So this is very popularly used, and we have another one which is a sigmoid function. So you have heard about it in my neural network videos. It's often used in neural network. So it computes a similarity using a hyperbolic tangent function. Now this is the equation, and this gamma and c have the same meaning. Like, this is a parameter that controls the influence of the training examples, and c is a constant, which is a hyperparameter, you can say. But this is not very popularly used, because this is mostly used when, like, the data distribution the data distribution resembles a sigmoid function, like your data distribution when it looks like this S. And very often we don't know, we usually don't have the domain knowledge, how the underlying data distribution is supposed to look like. So since it's a very specific scenario kind of thing, it's rarely used. And there's also another reason why sigmoid function is not very popularly used, because the matrix which is like the matrix which you get using the sigmoid function is not always a positive semi-definite one. Now the question is, why, or what is the big deal about this positive semi-definite matrix? Now let us quickly first address what is a positive semi-definite matrix. Suppose you have a matrix A which is of size n cross n, and how would you find out that if your matrix is a positive semi-definite? Now, if your matrix is a positive semi-definite one, it will, like, this particular inequation will hold, where x is basically an n-dimensional real valued vector. So now the question again is, why are we so, like, obsessed about this semi-definite thing? Now this is important because in convex optimization, the Hessian matrix, or the matrix of the partial derivatives of a convex function, is always positive semi-definite. Now this property is used to identify the local minima. And if your problem is a convex problem, you just have a single minima. So your local minima, whatever you find out, you can be sure that this is also the global minima. So in convex problems, basically there is more than one optima. Sorry, in convex problem, there is only one optima. I just said something different. Anyways, if it's a non-convex problem, there can be more than one, optima. So probably you have reached this solution and there is no way you can reach here. So you will have to present that as your minima. But probably you have this one which you could not reach somehow. This is the true minima or the global minima. So if your problem is a convex kind of problem, so in this case, the problem is the error problem. That is, you are trying to minimize the error. So if your error problem becomes a convex one, you can be sure that whatever minima you find out, that is going to be the true minima or the global minima here. So you can, like, there's more to this positive semi-definite matrix, and you can just Wikipedia it for more details if you're interested. Now we'll get back to the SVM. So we'll look at some of the regularization parameters used here. So first we'll talk about the parameter C. So this controls the trade-off between maximizing the margin and minimizing the misclassifications in your training data. So a small c creates a larger margin, but this might allow more misclassification, which will ultimately, like, it can lead you to underfitting. And then a large c has a smaller margin, and it penalizes the classifications more heavily, and this would also lead to a potential overfitting. Next is gamma. Now it defines how far the influence of a single training example has. So a small gamma means a large influence, and this will again lead to a potential underfitting. And if you use a large gamma, it will mean a small influence, and that will lead to a potential overfitting. So now we'll move on to how the support vector regressor works. So suppose this is your target variables, so there is just one kind of data because you are using regression, it's not a classification thing. So you are trying to find out the value for this target variable. So what we do here is we find a hyperplane that best fits the continuous variable while tolerating a certain amount of error. Of course, there will be some error. And so here we actually don't separate the data points, whereas the support vector regressor tries to fit as many data points as possible within this margin. And then it identifies the support vectors from the training data. In this case, the data points which is most closely aligned to this, and or the more relevant data points, as you can say, for defining the decision boundary. And the model uses these support vectors to predict values for new data points. So then it minimizes error between the predicted and the actual values during training. And of course, this process aims to find the best fit for the data. So there is not much which is used or said about support vector regressor. So I'll also leave it here. Again, if you want a more detailed explanation, do let me know about it. And now we'll talk about the advantages of SVM. So the first, a big advantage which I'll talk about is it is very effective in high dimensional spaces. It performs really well when the number of features is greater than the number of samples, which makes them very suitable for tasks like text classification and bioinformatics. And this is also robust to overfitting because this margin maximization principle and the regularization parameters, these make it really robust to the overfitting. Now, especially when you use a very high dimensional space, the chances of overfitting is really less. It's also memory efficient because it uses only a subset of the training data, that is the support vectors, during the prediction. The other data, it just forgets that. So this makes them very memory efficient. And this is also versatile with kernels, like you can use different kernel functions, so it can adapt to a wide range of data types. It can adapt to linear, non-linear data types, and it also supports complex decision boundaries. And then if you are using linear SVM, you can really the data interpretability is really clear because the decision boundary is very straightforward and can be easily interpreted. If we talk about the disadvantages of SVM, the first thing is the computational intensity. Now, training can be computationally expensive, especially if you're using large data sets. The training time complexity can typically vary between ON square to ON cube, where N is the number of training example. So this is the time complexity for training data. This is actually, yes, it really takes some time. And then we have sensitivity to parameter selection. Like the performance of this SVM is heavily dependent on the correct selection of hyperparameters. Now, tuning these parameters can really be challenging. Then if you have an imbalanced data set, it struggles with that, because especially if one class significantly outnumbers the other, it potentially biases to the model towards that majority class. Now, we'll see this in a while when I'll show you I'll use SVM on sentiment analysis. I'll show you this problem. And then we have like lack of probability estimates, because SVM do not directly provide the probability estimates for class membership. It just gives us the ultimate class prediction. So this also kind of makes it like a black box. Then if you're using non-linear SVM, like the decision boundaries are often complex and this is very hard to actually understand. Now, if we talk about SVM applications, this is widely used across the different domains because they are very effective in handling complex classification problems. So, first I'll say it's text and hypertext classification, like spam detection, topic modeling, classifying those news articles, sentiment analysis. These can be done. Next, we can use it for image classification, like image retrieval, handwriting recognition, face detection, then also object detection, like that. We can also use that in informatics, bioinformatics, like for protein classification, gene expression, then cancer classification, diagnosis of disease, and so on. Then we can use it for handwriting recognition. It can recognize handwritten records characters for data entry, and also for validating those signatures and things like that. It can also be used in time series analysis, where it can predict the future value. So this can be done using support vector regressors. And then it can also be used very well in medical diagnosis and prognosis, where it can predict the disease progression. It can also predict personalized medicine. And also one thing which I didn't mention here, it can also be used in signal processing, like for anomaly detection, then speech recognition, and things like that. So now we'll see how SVMs, or how good SVM classifier works on sentiment analysis dataset. So we will be doing a sentiment analysis using support vector classifier, and I have taken the dataset from here. I'll link that in my description box, this particular link. So here the data set has 3 classes. So 0 means hate, 1 means offensive, and 2 means neutral. So it's given in integers. So since this, okay, so we will be importing these libraries. So NumPy and Pandas for working on the data set. We'll be needing scikit-learn to import SVC, and natural language toolkit will be used to pre-process the data, and also we'll be needing matplotlib and seaborn for plotting the data. So these were the libraries which were imported. Now, since we have a substantial amount of data, so I've already actually run the entire thing, otherwise it will take a lot of time to pre-process and also a lot of time to train the data. And I wanted to show you some of the use cases. So I've actually done it beforehand to save some time. So this is how my dataset is saved, and this is how it looks. So this column is actually not in this particular dataset. So what happened was, I was trying to open that using Microsoft Excel, and I don't know how this extra column just got added to the original data set. So anyways, we are going to be completely deleting these columns. So count means how many people were actually employed to label the data. So this was the original tweet. It was based on, this is based on Twitter data. So this was actually manually labeled, this particular data set. So for this particular tweet, 3 people had actually they inspected the data, and 3 of them said that this is not a hate speech, not an offensive language. So, and hate speech, I think, if I remember it correctly, if something racial has been said, those speeches have been labeled as hate speech. Otherwise, when offensive language is used, that's labeled as offensive, and of course neither means it's a neutral thing. Say for example, if you take this tweet, that is number 4, so 6 people have actually worked on this data and 6 have termed this as offensive, whereas in this case 3 people inspected the tweet, 2 found that this is offensive and 1 felt that this is neutral. And since they went with majority, this was assigned the class 1, that is offensive. So this is how the dataset looks like. So what we will be needing is just the class and the tweet. We won't be needing these details like how many people inspected and so on. So if you go through the data types, why I did that, because sometimes you are given the class as 0, 1, 2, but then you find out that this is of type object. So this was not the case in this data set. It's given as int, and this is what I did to just check that if there are columns, if there are rows and columns which contains null. So this giving me 0 means like it's a clean data set that way. It does not contain any null data. And then I just dropped the unnecessary columns. Like these were the unnecessary columns. And now it looks like this, just the class and the tweet. Now these value counts give me how many offensive data, how much offensive data, hate data or neutral data are there. So there were actually the shape if you go through. So 24,783 tweets were collected, and here, so among them 19,190 are of type offensive, 4,163 data are neutral, and just 1,430 data is like hate data. So you can see that this data set is very, very imbalanced. So let's see how this SVC works on this data. So we need to clean and lemmatize the text data. So lemmatization means, suppose you have a word like eating. So that will be shortened up to eat. So these are actually reduced to the dictionary or base form, like better becomes good, or running becomes run, and so on. This is known as the lemmatization. So these are the functions. These are the functions you will get in Stack Overflow and everywhere. So this is a very what shall I say, a standardized function for lemmatizing your text that is done using NLTK, the toolkit, which I was talking about, the library that I imported. So if you want me to share this particular notebook, I will be doing that. So please leave me the note in the comment. And then this function actually vectorizes the data. As you know that when we are dealing with machine learning or any artificial learning, deep learning, whatever be it, computer understands numbers. It does not understand words or the natural language. So whatever we have to convert that to a real vector, and then computer, like artificial learning algorithms, work on that. So that is done using this count vectorizer from scikit-learn, and this was the actual cleaning and lemmatizing that happened here. So since these contained some special characters which you don't need, you have these usernames and these exclamation signs, RT and things like that, you don't need it. You just need just what the message was. So some text like tweet based cleaning had to be done. So this was done to remove RT. So these are all done mostly using regex. This was done to replace names with @, remove the HTML tags, and remove the punctuations, and then the case was changed to lower. This is also very important, so that because if you write something like in caps, the same word in caps and in lower will get a different vector representation. This is something which we don't want, right? So in order to um, address that, we need to change the case. And then we remove the stop words. So stop words are like the filler words, like the conjunctions, and then some articles like it. And these are like, if you go through English text, like the majority will be those filler words. These are also known as the stop words. So we also need to remove that to understand the context better. And then we just lemmatize and vectorize. So this is the final data preparation being done. And now we have applied the support vector classifier on the data set. Now first you will train, test and split the data using the train, test, split. So that I have imported using the word TTS. So you can see here from sklearn.model selection, sklearn for scikit-learn, import train, test, split as TTS. So generally you will see people using this train, test, split as a function. So I just renamed that to TTS. So I'm using TTS because sometimes, you have those typos and then you just, that is again, you have to type so much, train, test, split, underscore and things like that. So 20% of the data was kept as validation set. Now this is the first thing that I'll show you. Like SVC is the training, the model which is called. So I used kernel as RBF, that is radial basis function. And now I'll talk a little bit about the class weight that I've done. Just a moment. I just put this off. So if you look at this data set, you can see that this is a very imbalanced data set. So the easiest thing that you can do in order to address this imbalance is you can follow a way so that whenever during training your model misclassifies, so if it misclassifies the data which is not well represented, you can increase the weight of the data. And suppose there is a penalization, say, let me just put it in a very easy way. Suppose it's a hate speech. So and that is being say misclassified as offensive, since most of the data represented is offensive in nature. So what happens here is, say the penalization is X, some X kind of penalization is applied to any data which is being misclassified during training. So what happens here is, when I add some class weight, so 12 times of X will be penalized for misclassifying a hate data. So hate is represented as 0. So the penalization factor will be increased or multiplied by 12 times. Offensive data will be like 1:1, so just 1 times, like the original penalization factor. And for your neutral data, it will be like 4.5 times the penalization factor that will be imposed. So if you take a kind of, if you see the ratio, so this is almost 13 point, I think 6 times 1430, this offensive data. So I just went for 12. This is also, maybe I have taken a little bit more. It could have been 3 or something like that. So this does not really like factor 3 or factor 4.5. It doesn't make a huge difference. You can actually play around with this data and find out how the accuracy changes. And another thing which I would like to say is random state. I've used random state so that the same data set or the same train and test split is done every time. Because whenever I'll be using TTS, it will be randomly selecting data. It will be randomly selecting the test data and the train data. So just to make sure that the same train and test data is used, if I say if I use a number of algorithms other than SVC, maybe I'm using a neural network. So if I have to compare, I need to make sure that the same trained data and the test data were used during training and validation, right? So for that reason, we are using this random state. So here also I've used random state. Anyways, so this is your RBF, and when we see the accuracy between the original label and the predicted label, we find an accuracy of 0.8944 something. So it's around 89.44%. So 89.44% of data was labeled correctly. Now, by default, the kernel that SVC uses, if you do not use that parameter kernel, if you do not say anything about it, it is RBF. And just to show that, here you can see that I have added the class weight and random state, but I have mentioned nothing about the kernel. And the accuracy is the same, 89.44. Now moving on to this, suppose we are using a linear kernel. So the rest of the things is same. Instead of RBF, I'm using linear. So linear was on linearly separable data. And if you can see the accuracy here, it's 86.34%. So a good more than 3% change in accuracy. And this is pretty substantial change because in fact, when it comes to accuracy, we go for that 0.1, 0.01, even that also counts. So here 3% accuracy change is quite a big factor. Now, what if I do not use this class weight? If I use the original penalization, like if X is a penalization factor for misclassify an offensive sample, X will be a penalization. The same penalization will be slapped on a misclassified data if it's a hate data and it has been misclassified to be neutral or something else. So if I do not apply any weight, practically, the accuracy is 90.13. So I get a higher accuracy, like more than 0.5 accuracy, right? So that's pretty substantial. So you might say that, why are we using these weights? So it's better if we don't use the weight because we are getting a better accuracy. But here comes the main thing, like you will need to dive deep, like if it's worth. So here comes the plot insights. What is it? I'm showing you right now. So here I've just replaced 0, 1 and 2 with hate, offensive, neutral. So that way it's easier. Every time I don't have to actually go back and check, oh, what was 0, what was 1, what was 2 and things like that. So this is the normalized confusion matrix. So why am I using a normalized confusion matrix? By the way, if you don't know what a confusion matrix is, I already have a video on that. I will link that to the description as well. So why I use a normalized confusion matrix is because suppose you have, say, 3000 test samples, maybe 10 are hit data, maybe 2500 you have this offensive data and so on. So it will be difficult if you get the raw data. You will not be able to, you will actually have to go and calculate what was the percentage of data that was correctly classified and so on. So if I use the normalization, this will be done. I don't have to think about this. I don't have to actually do the manual calculation. I'll show you the raw confusion matrix. So this is the plot. So as you can see here, so this is done using this data, this data, using kernel RBF with this class weight and so on. So I'm using this widepred here. So coming to this, okay. So if you see this diagonal, so this is the data which is actually a hate data and classified as hate. This is the percentage or the ratio, like this was an offensive data and how many of those offensive data were labeled as offensive, and this was like true neutral data which has been labeled as neutral. So this is the true classifications, like this diagonal, okay. So as we can see here, so 34% of the total data, like the total hate data which was there, only 34% was classified correctly as hate, whereas in case of offensive, 92% were classified as offensive, and 94% of the data, offensive data, was classified properly by the model. And if you see here, this actually means that this was a hate data and this was predicted as an offensive data. So you can see here the true label and the predicted label. So the entire line, this was the hate data. So 53% of the hate data was classified as offensive and 12% were classified as neutral. When it comes to offensive, only 2.9% of the data were classified as hate and 4.6% of data was classified as offensive. And when it comes to here, less than 1% data was neutral data was classified as hate, and around 5.3% data was classified as offensive, like neutral data was classified as offensive. Now this is the confusion matrix of this particular the raw confusion matrix. So if you sum across the column, you will get how many hate data was there in the test data set. So summation of 94 plus 146 and 34, this will give you the number of true hate samples present in the test data, whereas 112 plus 3523 and 177 were the count for your offensive data in the dataset, and 8 plus 46 and plus 817 were the neutral type of data. So if you see here, if you go by the diagonal, so only 94 94 rows were correctly identified as hate, whereas 3,523 labels were correctly identified as offensive and 817 labels were correctly identified as neutral. So these actually, this is 94, 3523 and 8 plus 817 is other actual number of data which were correctly identified. Rest, everything was misclassified. So always remember this diagonal, this one. Okay. Now let's move on to this data set, this model, which gives us a 90% accuracy. Let's look at the confusion matrix here, the normalist confusion matrix first. Look at this. Just 8.8% of your hate data was correctly identified as a hate data, whereas 78% of the hate data was identified as offensive and 13% as neutral. And here when you come here, so this is the true column. So 0.95, that is 95% of the offensive data were correctly identified, and this remained the same, 94%. So if you come have a look here, so this was just 92% were correctly identified, whereas this was 34% of the data was correctly identified here. But the thing is, when you talk about accuracy, it will be based on the number of samples correctly identified. So if you go through the true confusion matrix, the raw confusion matrix here, so 3,628 offensive samples were correctly identified. Just 24 samples here were correctly identified and 816 samples were correctly identified. So this is almost same. This is 817 here and 816 here. So, and this is 24 and this is 94. But if you now consider this factor, so 24 plus 3628 plus 816, this is higher than 94 plus 3523 plus 817. And since the total number of samples correctly identified was greater in this particular by this particular model, so therefore you get a close to 90 accuracy here, 90.13 accuracy here. But if you look into the model, this is a more balanced thing. Like 34% data was still okay, but here less than 10% of hate data was correctly identified. So this is something which I say that this is one of the disadvantages of SVM is if your data set is imbalanced, it will this will have a natural tendency to always select the like the class label as the one which has a majority. So since here offensive is the majority label, so 78% of data was identified as 78% of hate data was identified as this offensive, whereas this 13% of the data were identified as neutral. This is for the 90% accuracy model. And if we look here, see, just 53% data were identified as offensive, whereas 12% data was identified as neutral. So this didn't quite change. It was 12%, it's 12% here and 13% here. But look at this, 78% here. And since I just used a little tweak just to penalize the hate samples, misclassification of hate samples more, 53% was the value which were misclassified. So now if you just look into the classification report like precision recall and F1 score, so this you can just take a screenshot. Sometimes I also forget what is a precision and what is a recall. So of all the items labeled as positive, how many were actually positive? This is your precision. And of all the actual positives, how many did the model correctly identify? So this is your recall. And this is the F1 score. Just remember this one. F1 score equals to 2 into precision into recall divided by precision plus recall. So try to remember precision and recall. So all the items labeled as positive, how many were actually positive, and of all the actual positives, how many did the model correctly identify? So it's a true positive. So if you look into this, this is based on that 89%, that is a weighted SVC, because clearly we are rejecting that model because less than 10% of the data. Now this was okay, a benign kind of a data set, hate, offensive, whatever, it won't really matter a lot. Like offensive, hate, both are harmful. Maybe hate is a little more harmful. But if it was a medical data set, suppose you are dealing with a data set that contains some rare disease, maybe just 1 out of 10,000 gets that disease. So definitely that data set is going to be a very imbalanced one. And you can't really, it's difficult to actually balance those kind of data set. And if this kind of misclassification happens there, so it will be like a Newsys model, right? So always, whenever you are using whatever model you're using, it might be a machine learning model, it might be a deep learning model, always do this confusion matrix, because that gives you an idea of how it is doing or how well it is classifying the less represented classes. So always go for it. Okay, so this is coming back to this. So 44% is the precision. So only 44% of the data were true, like truly identified. So 56% of the data were misclassified as hate data. Just 44% of the data were the true hate label. And here 0.34, that is, we had 34% of the recall. Like this says that of all actual positives, how many did the model correctly identify? So just 34% of the data were correctly identified. And then you were, and this is your F1 score, which is 0.39. When it comes to class offensive, so you will need to see this color map. So This is above 90% of the data have a precision of like this offensive data has more than 90% precision, and the recall is between zero point 0.8 and 0.9, somewhere over here, I think, somewhere over here, close to 0.9. And this is also between 0 0.8 and 0.9, or maybe just it might have just touched 0.9 or so when it comes to recall. And when it comes to neutral data, the precision is not that great. It's between 0.7 and 0.8. It will lie somewhere here, maybe 0.75 is the precision. And recall is a little better, maybe close to 0.9, or maybe a little bit more than 0.9. And when it comes to F1 score, it's between 0.8 to 0.9, maybe 0.83 or something like that. So this is the entire how your SVC actually classified the samples, and this is how you will use SVC when you're using scikit-learn. Of course, all of us will be using scikit-learn for this. And that's all for today. Hope you had learned something, and please do check the description box for all the data set and stuffs. And if you want this particular notebook, please leave me a comment. I will upload the notebook so you can download that and have some fun with playing around with this data set. So that's all for today. Thank you for watching.